invented by Ozsvath and Szabo in 2000. And for every, it associates Z2, a graded Z2 vector space for every stream manifold. Okay, this is the easiest version. And the way it does it is that it associates the homology of a chain complex. So if you have a stream manifold, then you can always describe it with its Heegaard decomposition. The Heegaard decomposition divides your stream manifold into two handle bodies, and the two handle bodies can be described by curves that are trivial in the handle bodies. So for example, if I want to describe the handle body which is visible here, then I would do this, and then if I want to describe the handle body which is outside, I'm trying to draw a Heegaard diagram for S3, then I could do this and this. I just didn't want to make it completely trivial. Alright, and then the generators of Heegaard for homology are intersections of these blue and red curves, exactly G of them, so that on each blue curve there is exactly 1 point, and on each red curve there is 1 point too. So it's G tuples. G is 2 in this picture. G tuples of intersection point. Of blue and red curves. So this gives you a chain complex. Once I define a differential, which I'm not going to do, the differential counts holomorphic curves. So and it counts holomorphic curves in some symmetric product of this space, and the holomorphic curves have this boundary condition that. So actually, by curve right now I mean this. So that this part of it is mapped to the red curves. This part of it is mapped to something which is associated to the blue curves. So then this is mapped to two intersection points, and that's fine. And that's mapped into the symmetric product. And this condition. So whenever you have such a holomorphic disk in the symmetric product, you can always project it onto your stream manifold, and the projection is going to look similar. So like for example, any curve which leaves this point has to have a red curve on its right and the blue on its left. So meaning that you can only start going this way or this way. No holomorphic curve is going to start this way or that way. This is something I'm going to use. And then there is one more feature of Heegaard for homology, and this can also be generalized for knots. This was done by Rasmussen and independently by those two guys, Ozsvath and Szabo. And then the way it goes is that if you have a Heegaard diagram, I'm going to do again a Heegaard diagram for S3. That's the only thing I can do. So I have a Heegaard diagram for S3. Then, if you remember, even here, you have to for this theory to be well defined, you have to specify a point in the complement of the alpha and beta curves, and you only counted holomorphic curves which somehow did not intersect this base point here. So, like for example, if I put my base point here, that would not let this holomorphic curve to start. So then I would know that there is only one direction of holomorphic curve, and you can start from this intersection point. And here, instead of 1 point, I'm going to specify 2 points. Maybe these two, so that it's also in the complement of the alpha and beta curves. But I want to make sure that, no, actually here it's not so important. So the way it specifies a knot for you is that you connect these 2 points in the complement of the alpha curves. So when you don't see the alpha curves, then you can just, I'm going to screw this up. Yeah, so you connect them in the complement of the alpha curves and in the complement of the beta curves. So like here, this should be in the complement of the alpha curve. No, on the beta curves, sorry. So like this, it can, it can go around like this and then go back. And then when you want to cross in the complement of the beta curves, of the alpha curves, you can just do this, go around again, no, the other way, and then finish it like this. And then you need to understand what these crossings mean. Like one of them, you think of being in the alpha handle body, and the other one being in the beta handle body. And then you can make sense of these crossings. And what I drew here is that this is going to be the right-handed triangle. I hope. If, like I assume this is the type of person you have to make sure. And then just exactly the same way you do it here, the intersection points are going. The g-tuples of intersection point is going to give you the generators, and the maps are the same. And I'm again talking about the easiest theory. In the easiest theory, you count the same type of holomorphic curves which do not intersect none of the base points. So it does not intersect any of the base points. So here, here that probably is no holomorphic curves. And then that's it. I could do harder series. It's just, I think it's not necessary. And actually, all my theorems which I'm stating, they work in other series if you want. And then, so you can think of this in another way. If you let the points have names. One of them is the C and one of them is the W, and you can think of this Heegaard Floer homology either just the original Heegaard Floer homology with an extra grading given by how many times you cross the W, or you can think of it as its associated graded object, as what I just said, when you don't let the W to be crossed. And so meaning that basically any knot you have gives you an extra grading on your Heegaard Floer homology, and that extra grading is called the Alexander grading. Another way to think of the Alexander grading is to do zero surgery on your knot, and then if your knot was null homotopic, which is in S3, then if you cap off your manifold, then the Alexander grading of a point can be evaluated as the spin C structure associated to the generator evaluated on the cap-dot surface. This is the cap-dot cipher surface.
X is a generator?
Yeah, X is a generator. So it's a g-tuple of intersection point. And then there is as chat I told you, there is a spin C structure associated to every generator. Just by looking at the vector field of which is the gradient, and making it non-vanishing by the on the path is specified by this base point here, by this point there. And then, okay, so that's all I wanted to say about Heegaard Floer homology. And then I will talk a little bit about contact structures, really just a little bit. I mean, because you heard a lot. So a contact structure was again vector plane field, which was which was nowhere integrable. And one way to specify a contact structure is by open book decompositions. And I'm not completely sure that was described here in this conference. Was it? Open book decompositions? Okay. So, okay, very good. And I'm only stating what I need for an open book decomposition. So for me, an open book decomposition is going to be a surface with boundary and a monodromy, which brings, so I have a surface which has a boundary and a monodromy map. So this map is a diffeomorphism of the surface which leaves the boundary of the surface unchanged. And then I'm thinking of a stream manifold as a mapping cone of this surface with the monodromy map, and identify all of every point on the mapping cone, which is in this S1 family. And then so let's see what we have here. So if I have an open book decomposition, then it gives me, sorry. So here is my open decomposition. And when I form this mapping cone, it's an S1 family of these surfaces glued to itself by the monodromy. So if it's an S1 family, I just take half of the S1 family, and that's going to give me the surface across an interval, and with all of these points, which are the same on this interval. So the interval across this point identified. So all of these points are the same on each surface. So meaning that I have this surface cross interval here. This is the boundary of it. So this point is identified with this point here. That's why I do it to the same spot. And then, so this one actually gives me a Heegaard decomposition of my stream manifold. The way you see that it gives you a Heegaard decomposition is that you first subdivide your surface into a disk. So you drew arcs on your surface that it gives you this, and then when you take these arcs across an interval, divided out by the equivalence relation, then these are going to, so arc cross interval, that's I cross I, and then you divide out by some equivalence relation. So this is I cross I. This is the mapping. This is the original I direction. This is on the surface. Then you divide out by gluing all these points together. That's still going to be a disk. So this is a handle body. This means that this thing up is a handle body. Okay, so I can just draw the other part of it. It looks like this. And then on the bottom part, you have the same picture. So you have your surface cross the interval, and again it's going to be a handle body. The only thing which is interesting about it is because you have a monodromy, then the image of these curves here are not going to be the same as when you do it upwards or downwards. Okay, so here I can think of my monodromy to be the identity, but here I will think of it as actually the monodromy. Okay? So I subdivide my monodromy in this way, that it gives me free, but at the beginning it doesn't do anything. So then let me just draw the same picture, just I'm gonna perturb my curves a little bit so that it's more visible. Okay? And then the image of this one is brought somewhere by the monodromy. Maybe this one doesn't change it at all. And then, so I perturb these curves here so that they intersect exactly in one point. And I also impose an orientation which on which way I perturb it. I'm going to explain it in a minute. So let's look at this picture right now. So this is a Heegaard decomposition of my manifold because the red curves specify what are the things which bound the disk in the upper part, and the blue things specify what are the disks which bound disks in the lower part. So this is a Heegaard decomposition of my string manifold, and on this part I intentionally made it in a way that these things don't that there's exactly one intersection point on this part, and this, let me call this is a special element in my chain complex associated with the string manifold, which a priori, I mean, it depends on my picture, but let me just let's think about it. And then the curve has to go this way out from here, or this way. So if I put a base point here, this isn't the disk, then there's going to be no curve coming out from this element, meaning that it's going to be an element. It's going to define you a chain. And then so this is going to be an element in my Heegaard Floer homology for the string manifold, and as it turns out, this was proved by Honda, Kazin, and Matic. This element is independent of how you chose your open book decomposition and how you chose the curve there. So this element is called the contact invariant. So finally, this contact invariant was not originally defined this way. There was an earlier definition of the contact invariant by Ozsvath and Szabo, which used a different version of Heegaard Floer homology. Basically, what it said is that the binding of your open book, so which is the boundary of the page, gives you this extra grading called the Alexander grading, and they proved that in that grading, in the grading, which is the bottommost with respect to this grading, it's generated by one element, and the contact element was defined as that one element as living in the Heegaard Floer homology. Okay, so this is the image of the generator of the bottommost Alexander grading in age of K with respect to the binding. And these two agree, as it was proved by Honda, Kazis, and Matic.
Yes. Do you want to change the orientation of Y?
No, I didn't want to, but I read it. Yeah, you have to change the orientation of Y. So that it's not going to be apparent by if we could do that. Yeah, we do need to change the orientation of Y. But then this Heegaard diagrams actually not the cardinal.
Yeah.
So I'm lying a little bit. And then, so the reason we like this contact invariant is that it actually tells you a lot of things about the contact structure. So if you have an over-twisted contact structure, then the contact invariant vanishes. And if you have a Steinfeld-level contact structure, then the contact invariant doesn't vanish. Also, this contact invariant has some graded, some twisted versions, for which it's even true that if it's over twisted, then it doesn't vanish. I mean, for some twisting. And then there is another important property which says that if C has a zero torsion, then the contact invariant vanishes. And this give us, I don't know, second or third proof for the fact that things which have zero torsion are not Steinfeld-level. I think the first was given by David. Is it right? Okay. But still, it does use things. And then later on, they wanted to understand a similar type of invariants for Legendrian knots. And there were several approaches which I will try to so you have invariant for Legendrian knots. And transverse knots. Can you see it from there? Hmm? So the second one, the second invariant of this type was actually exactly copying this definition. So if you have a Legendrian knot, then you should know that it's possible to put it on the page of an open book. So knot can be put on an open book. So meaning that I have my Legendrian knot, and it's gonna sit somehow. This is usually green on the page of an open book. And also you can make sure that the way it sits is not trivial. Okay, so it's homological and interesting curve there. Meaning, so once it's homologically not trivial, you can make sure that one of the, so if it's homologically not trivial, then you can draw a curve which intersects it in one point. And then after you drew this one, you can draw the other curves that they don't intersect it at all. Okay? And then if you remember, I'm just copying that picture, and I'm constantly lying about the orientations. I'm sorry for that. So then you remember one of the base points were sitting outside of everything in the disk, and I'm gonna put the second base point, which describes the knot, here. Okay, and then if you remember how it was defined, you connected everything in the complement of the blue curves, that's here, and you connect everything in the complement of the red curve. So these 2 points do describe my knot. And then, so they describe my knot, and again, by the same argument, they give me if I choose these generators, I'm not. So this picture has another side, which looks exactly like that. So by the same argument, this left-hand side generator is a chain element. So it defines me an element in this case in the Heegaard Floer homology of my symmetrical with respect to K. So this version was given by Lisca, Ozsvath, Stipsicz and Szabo, and it's usually called as loss invariant because of their first letters. So that's one version. You can do another version which is totally different, which is called the grid invariant. So Heegaard Floer not for homology has a version. So it has a version where everything is very simple, and the Heegaard diagram is a torus, and the things which describe your knot are lying on the torus, and you have several of them in this case. So let me draw a picture. So here's my torus. So everything is identified the way it should be, and then so this is going to be one alpha curve, red curve, and then in the middle I have some number of alpha curves. So this is just one curve, and the rest is 1, 2, 3, 5. You could have any number. And then you have the same number of blue curves. So this is 1, and then so this describes your node S3, your S3, and then the node is described by these base points. So here and here. So the way it gives you a knot is that you connect in the complement of the red and the red. In each complement, you want to have exactly 2 of the points. So here, it's these 2. Hmm?
You missed one of that.
Really?
The third column.
Oh. Okay. So you connect everything in the complement of the reds, and then you connect everything in the complement of the blues. And these are all going underneath. I'm arbitrarily changing the orientations whenever I need to. So the way they describe the Heegaard diagram, that's going to give you some way of over and under crossings. And I actually made it consistent to my talk, which is not consistent to the usual way they do it. There's an over and under crossing information. And then you rotate this diagram. If you look at this diagram from this side, then what do you see? First of all, I'm going to smooth these parts out, and I'm going to make these 2 cusps. And then it's going to look like exactly a Legendrian knot. So is this right? Okay, it's the same. Just looking from this direction. And then, so every grid diagram describes me a Legendrian knot this way. And actually, every Legendrian knot can be described by a grid diagram. And the grid diagram gives you Heegaard for not for homology. So if I specify an element here, then that will give me something. So let me specify the element, which is the upper left corners of the axis here. Okay, upper left corners of the axis.
This is where you're changing orientations.
Sorry?
That's the other right? Like you change orientations.
Well, left, upper. Yeah, that's right. Okay, but actually I drew the wrong ones. I wanted to draw left. Okay, so upper, left, left, yes. Here you go. And then this point is the same. So here, these are the same points, and upper left, this one, and then this is the same point again. Alright. And then, because if you're not allowed to cross the axis, again, any holomorphic curve which would start, it would start this way. So it cannot start because you're not allowed to cross these points. Okay, meaning that this is again an element in the chain, and it's going to be an invariant of your Legendrian knot. You just have to check what type of moves it remains invariant of. And this is a result of Ozsvath-Szabo and Thurston. Okay. And there is actually a third invariant, which I was going to describe, but I think I'm not going to. So that's an invariant for the knot complement in a different version of Heegaard homology. And then, so here are these invariants. And when you use this invariant, it has lots of properties which are useful, which are written. Okay, so if you have a contact structure which is over, so if you have a knot whose complement is over twisted, then this invariant vanishes. So this is called L hat, corresponding to Legendrian knot, and this is called lambda hat, also corresponding to Legendrian manifold. So this vanishes, and if it contains U retorsion. So first, okay, so this one was proved. Oh, I think it was proved by the original authors. So it contains U retorsion, then it vanishes again. That one was proved by Shea, Vela-Vick, and Stipsicz and me. And then there's another thing for which I just first need to define something. So if you have a Legendrian knot, then as John Etner was talking about, you can always make a transverse knot which is close to it. And and if you have a transverse knot, there are Legendrian knots which are close to it. And there is a relation between Legendrian knots that are close to transverse knot, and that's the following. So if you have a transverse knot, then the Legendrian knots that are close to it are all related by these type of moves. So this is called negative stabilization. So by this I mean that if you have a transverse knot and you have two Legendrian knots in its neighborhood, then those two Legendrian knots are going to have a common negative stabilization. So you might need to apply this several times that are Legendrian isotopic. So common negative stabilizations that are Legendrian isotopic. And if you look at this picture, then this invariant remains unchanged under negative stabilization. Okay, let me just write this. So if you had, they are not here, then this is called L minus. And then this notation is different from what John used, I see.
What is the orientation on that?
You introduce downward clasps.
Yeah,
No.
Then the other way. Take the other way.
Okay, then upward clasps. Okay. Well, after I change so many orientations, I don't think it matters. So lambda of L minus is going to be the same as lambda hat of the original one, no matter how many times you do it. So this means that because every transverse knot can be described by these knots which are in the neighborhood, and they are only related by this only one operation, then this invariant is going to give you automatically an invariant for transverse knots. And if you think about it, this is actually nothing more than a transverse invariant. So if you have an invariant for transverse knot, so this invariant is defined just by taking L lambda hat of L for any approximation of it, and that's going to be the same thing. And once, if you just in theory have a transverse invariant, then you can always define a Legendrian invariant which has this property. So these are sort of equivalent notions. And the same is true here. So this is invariant under negative stabilization. So it gives you an invariant T of T. Again in Heegaard Floer homology, which is a transverse invariant. And you have this transverse invariant, and then here's the third statement I wanted to state about it. So if you have a binding of an open loop, then this invariant is never vanishing. Meaning that the binding of an open book, even in an over-twisted contact structure, must pierce every single over-twisted disk. I think this is the only way I've seen this proved. So the way, this is a result of Shea, and the way he proved it is that basically he defined, he realized how you can see, if you have a Legendrian knot, how you can make a transverse knot out of it. So let me try. No. So if you have a transverse knot, how you can realize it, how you can easily see its Legendrian invariant in Heegaard Floer homology. So I have a then this is a Faulkner's theorem, which was, I think, maybe proved by Vincent Collin, and right now it's written in the paper of Lisca and Stipsicz, that every transverse knot can be put as an open book, as a binding of an open book. Maybe the open book can have other components, but it can be a binding component of an open book.
So the result of Shea is that if it's the entire binding, right?
I think after that, Etmeyer and Shea, they have a generalization which says it's for anybody.
No,
No,
it is
for link.
Oh,
it is for disconnected binding, but the whole binding has to be.
Yes. So if you have a disconnected binding component, there's a link version of homology, and that one cannot be zero. So it can be and then let me draw a picture. So here is my transverse knot, and right now it gives me. So this is a boundary of one page of an open book. And there is an operation of open book. So whenever you have an open book here, you can just introduce a small, this is something local. So this is a small knot, which is the meridian of my original one. And then the open book, which is defined by this page, is going to give you the same contact manifold. So that describes you the same contact manifold. That's something you have to check locally, and that's it's not so easy actually, but you can do. Yeah, that changes my. So if I had the page of the open book here, then if I don't care about the embeddings, then the new page is going to look like this. Okay. because this is just twice twisted. And then when I try to, so the reason you have to do this, first of all, because when you want to realize a Legendrian push-off of this transverse node on this page, it's not possible. You need to have something more. It has to be something not boundary parallel to be able to Legendrian realize it. And here, the Legendrian push-off is not boundary parallel anymore. You can just realize it as this here, and this is realizable. Okay, so that would be, oh, that was green, sorry. That would be this curve on my picture, all right? And then if you remember how the definition of this invariant went, then it was. So this is the other part of the page. I imagine that this part is glued to this part, and this small part is glued to that part. I could actually draw a better picture, but I'm not going to. Then I used one curve, which intersected my node once, and I use another curve here, which is just the image of it under the identity. And then I took this blue thing, and here the image of this. So this is going to be actually a Dehn twist along this boundary component, and this Dehn twist is going this way, which looks like a, I guess it looks like a left-handed Dehn twist, but I'm upside down, so it's a right-handed Dehn twist. Okay, and then if you remember, the base points were, one was outside and one was inside, and I don't care about the other part. The other part remains the same as it was beforehand. And then using this theory, you can prove that it's not the same. And then somehow there is another thing I wanted you to see here, is that, so this thing, what I drew here is actually a braid. Oops. Okay, it's braiding along this axis. And I can draw this axis here on my picture. And when I look at so this Alexander grading I was talking about, with respect to this axis, it can be given as the winding number with respect to this thing. Okay, so the Alexander grading is the same on this picture as the winding number. So if I want to take the bottommost element, as people did, as Ozsvath and Szabo did for the contact invariant, then I have to take something which lies here. That every component of it on these lines lie inside here. And because it lies inside here, then the rest has to lie on this square. And you can check, it's actually not so hard, that the homology, when you restrict it only to this type of thing, is generated by one element. And that one element can be taken to be exactly this element, because that at least lies there. Okay? I mean, once it's proved that it's one element, we know that this is a non-zero element, and then it's done. So that's one observation about the grid invariant, that it lies, this is actually the bottommost, this lies in the bottommost Alexander grading, and well, I said something not completely true, and only the topmost of grading of this bottommost Alexander grading is going to be generated by one element, and I'm going to take that element, and that's going to be this one. so this property is here, and here I have a nice property that somehow you can see that this is given for transverse braids. And when you look at braidings, that's also some of the transverse property. And what we're going to do is that we link these two pictures. We're going to define an invariant which is purely for transverse braids and prove this property for everything and see that it's the same as this one. So, and then by doing all of this, we will be able to prove theorem that these two invariants are the same. And surely, under some identification of the Heegaard Floer homology. So there's an isomorphism of the Heegaard Floer homology, which brings this element to this element. That's what I want. And as I said, for this, I'm going to define an invariant for transverse knots. So this is an invariant for transverse braids, and fortunately, someone already did the work for us, and proved every theorem we needed for transverse braids in any complex structure. And then she was Pavel's group. So Pavel's group. So she has a result which is the Alexander's theorem for braids, that if you have a transverse braid, if you have a transverse knot, and then you have any open book, then you can always take a transverse isotopic copy of this transverse knot, so that it's going to be transverse to all of the pages of the open book. So it can be made and then also that's the Alexander's theorem for transverse braid, and then you want to have a Markov theorem also for transverse braid, and she also proved that. So if you have if you have two transverse braid, braids with respect to some open book, with respect to an open book, are related by basically, if they describe the same transverse knot, they are related by the following moves. So one of them is just conjugation, that you cut the braid in a different part, and the other one is that you have a braid here. So this is the axis, and this is the one component of the braid. This is again a local picture. Then you can make an extra crossing and do it again. But this crossing has to always be positive because it has to remain transverse. So any two transverse braid describing the transverse knot are related by this type of moves. This is called, unfortunately, this is again called positive stabilization of something else, which is a braid right now. And then using this theorem and the theorem of Giro, which gives you which open books describe, give you the same string manifold, you can have a relation between any two transverse braids in any open book which describe you the same transverse knot. And the open book is related by stabilization, and the braids are related by stabilization again, a different stabilization. And then, so if you have a braid and it's transverse to all of the pages, then it intersects the pages in the same number of points. So again, I can only draw one type of page, so that's going to be this one, and then it intersects then my braid intersects the page in some number of points, maybe 3. And then I can make sure, so I have this mapping cone construction for the entire stream manifold, and I can just perturb this mapping cone a little bit so that the braid itself is going to be the mapping cone of these 3 points. It's going to be, so then the diffeomorphism I'm talking about is a diffeomorphism of this thing, of this page, which leaves the boundary unchanged, and which leaves these 3 points setwise unchanged, so it can permeate the points. And then I again just do the same thing. I divide my page up into several lists, each of which containing exactly one of the points of the intersection with the braid. And then, very surprising, you take these other elements, and you again define your invariant to be the intersection which is on this side. And then on the other side, oh, you only have one. So you also have this point. And you take the red curves to be the same, and the blue curves to be given by the monodromy. So these are the images of the other blue curves given by the monodromy. And then this element, again, because I have an element here which cannot be crossed, it's going to be it's going to define an element in the not-free homology, and that I'm going to call the transverse invariant. And then there is one thing I wanted to tell you about this, is that, first of all, so why is this good? So that's our theorem that this one is independently of all the choices you make, it's going to give you an invariant only on the transverse knot. It's not dependent on the braid itself. So you can take your braid and make it to have to be a braid with respect to the open book, which is the disk open book, the trivial open book for S3, or you can make it very complicated and make sure that your transverse knot only intersects your open book only once. So let's look at this picture. If I take
T and K is something.
Sorry?
T and K are the same.
This is a transverse representative of this guy. So they are smooth the same. So if I take a copy of this thing, then you can see that it intersects my page in exactly one point. So if I draw the Heegaard diagram I described there for this special case, then the page is going to be the same as I wanted. I'm almost done. And then my knot is going to be described by something which sits on this element, and then actually the monodrome is exactly the same because I only have one thing. And then so let me just draw the curves once more. It doesn't matter which side. Let me just try to copy. I know it's right. Yeah. So let me just put it a little bit here. So it's red, and then the blue was going this way, and then the blue was doing this. Sorry. can always make sure that these are close to the boundary point. And then do that. Okay, that's not right. That's not even this. That is the same picture. Okay. And then so when you take this element, it's on the same place as here. Okay? So meaning that it is exactly these two diagrams on the nose describe the same Heegaard diagram. And the element is exactly the same in the exact same Heegaard diagram. So this means that the loss invariant, that was denoted by T of T is the same as this small t of T. And then because this invariant has these properties that it sits in the given Alexander grading and Master grading, it's the same. This thing is the same as the transverse invariant for a transverse knot in the standard context structure. And so good series proof. And that's it.
Any questions?
So in Heegaard Floer theory, are there any real Legendrian invariants?
I don't know. Probably not.
Meaning that are not that are sensitive to negative stabilization.
I mean, okay, so there is this invariant which is in the knot complement, which is given to the knot complement, and that's, I don't know, I mean, that might be something which you can read of Legendrian information. It at least, you can see it for both orientation of the knot. So there is actually a real Legendrian invariant, which is the pair of, so if you have this invariant and the opposite orientation of the same thing.
Yeah.
So that pair do distinguish. So there are examples where this one distinguishes things in Heegaard Floer homology.
And the sutured invariant is zero for stabilization.
Is it? Wait, the suture. It's not. It's zero once you fill it in and get this one.
I think it's
I don't know. There maybe. For negative stabilization? I don't.
or maybe it's not.
Okay.
Any other questions? No, thank you.